pH neutralization processes are typical industry processes in relation to environmental or compliance requirements. Changes in pH can modify the concentration of other substances in the water, modify the level of toxicity. Decreasing can increase the amount of soluble mercury in the water, while increasing can cause the conversion of non-toxic ammonia into a form of toxic ammonia. Therefore, it is extremely important to be able to control this process so that the pH value remains at 7, that is, neutralized. For this project, the model of a pH plant from the University of California is used.
The purpose of this work is to design a predictive control model, an MPC, to control a pH neutralization plant. That's why, to achieve the objective of controlling the formation process, the pH neutralization plant was necessary a mathematical model based on input and output data, a data-driven technique. Therefore, for the modeling of the plant, which is highly nonlinear, it was implemented the Wiener modeling technique, which consists of a cascade connection of a linear block, which represents the dynamic of the mixture of the region, and a nonlinear block, which represents the nonlinear titration curve that gives the pH, which is found as a function of the chemical components having used. However, the MPC is implementable if it is applied to a linear system, which is obtained by putting the pH output in series with an inverse nonlinear block, which it is obtained from the Wiener model. It is important to know that the inverse nonlinear block is placed here and also in the input with the reference.
Now the question is how to identify these two plots. For this we have to design two signals, the pseudo-random binary sequence and the pseudo-random sequence. These two signals are defined for time to commutation, is that to see the frequency, which is the same for both, and the two values of the PRBS, which is binary. And also these two values define the range values of the PRS. In this case, the two-bus item was used for identification of the linear blood first space states, and the two values of the PRBS were selected by trial and error method for getting a figure around 70% in order to get a good control performance. So once you got the state space, we use the PRS to get the input-output data for the identification of the string learning machines, following the next instructions, where the output obtained from the state space will be the input data of the string learning machine, and the output of the string learning machine will be the output data obtained from the pH plan. However, the real goal is to get the inverse nonlinear blood, and all we have to do is to make a change between the input and output data from the string learning machine, and that we get another string learning machine that it will represent our inverse nonlinear blood, and this is how we can get these two plots to design the model predictive control.
For the tuning of the predictive controller, unlike the PID controllers, the cost function is used, which relates the set point with the control variable. The prediction and control horizons represent the prediction depth. Delta relates quality and lambda energy. For the process in question, the controller was tuned with the help of a MATLAB card, obtaining the best result for a prediction horizon of 20, delta equal to 1, control horizon of 3, and weight factor of lambda equal to 0.05. Using the MPC control described above, we can see that for a small pH variation between 6.5 and 7.5, there is an adequate control without oscillation and with a settling time of 50 seconds. By adding a white noise to model the measurements noise of the sensor, and readjusting lambda values to avoid sudden change in the control variable, an adequate control is achieved for graded variation in pH between 3.5 and 10.5. Here, the nonlinear behavior of the system is appreciated. Control is still good for two disturbances of plus 50% and minus 50% from the AC flow. Now, if we compare the results with the PID, it shows that it has a similar response from the pH signal, but from a physical point of view, the MPC has better performance due to the fact that it presents a more continuous behavior of the manipulable variable, whereas in the class L PID it presents large fluctuations in short periods of time, making it unviable. The set point is not even reached. Thank you.